This is Math 251, and we're in section 13.5, part A. I divided this section into two parts because we're still going to be looking at triple integrals, but in two different coordinate systems. In part A, we're going to be looking at what are called cylindrical coordinates, and in part B, we'll look at spherical coordinates. So for right now, the cylindrical coordinate system. The nice thing about the cylindrical coordinate system is that you actually know a lot about it already, because all it is changing to polar coordinates in one plane and then tacking on the third variable. The most common situation we'll encounter is that the xy plane becomes the polar plane, and we end up using z as our third variable. Let me show you what I mean by that, using a little diagram here. Let's see if I can make that small enough that you can see it. There we go. So this over here is our cylindrical coordinate system. And you can see that in the xy plane, we're using r and theta instead. And r and theta mean exactly the same thing that they've always meant in polar coordinates. R is our distance from the origin, and theta is the angle with the positive x-axis. So we locate this point here, Q, in the xy plane, but using the variables r and theta instead. Z doesn't change. Z is still z, so we just move up by z units to get this point P. So instead of referring to P as xyz, we'll now refer to P as r theta z. So in the cylindrical coordinate system, points are referred to as r, theta, z. Because again, r and theta are the usual polar coordinates, all of the things that you already know about converting still hold true. X is r cosine theta, y is r sine theta, and again, z doesn't change. We also have the reverse relationships. X squared plus y squared is equal to r squared. Tangent theta equals y over x, and once again, z is z. Now you might ask, why bother? And the answer is the same as it was for polar coordinates. There are certain shapes that are particularly easy to express, and in fact work with, when they're expressed in polar coordinates. So we're going to start by taking a look at a few of those shapes. First of all, we have the circular cylinder. X squared plus y squared equals c squared. Remember, in the xy plane, that would be a circle of radius c, but three-dimensionally, that would be extended parallel to the z-axis. So we end up with the cylinder. And technically that would be extended both up and down, but just to keep my diagram a little bit neater, I'm only showing it going up. All right, what would that equation look like if I changed it to cylindrical coordinate system? Well, the x squared plus y squared, always a dead giveaway that polar is a good choice, right? That's just r squared. So I'd have the equation r squared equals c squared, and therefore r is equal to some constant. By the way, to make things a little bit easier to work with, we typically restrict our r values to positives. We'll only work with r greater than 0 in the cylindrical coordinate system. So when I took the square root, I just took the positive square root. So if you've got an equation, r equal to a constant, you'll know immediately that that's simply a cylinder of radius c. All right, another equation that's particularly simple is the vertical half plane. Y is equal to c times x. Once again, if I imagine what that looks like, y equals a constant times x is just a line through the origin in the xy plane. So perhaps some line here. But then because z is not mentioned, I would imagine extending this again parallel to the z-axis. It would go both up and down, but I'm just going to show the up. And I end up with that almost like a door that's been opened, a plane that's been swung open from the x-axis. I call it a half plane for a reason, and I'm going to get to that reason after we do the conversion into cylindrical coordinates. If I manipulate this equation just a little bit by dividing by x, I'll get y divided by x equals c. But y divided by x is the tangent of theta. And if I simply took the inverse tangent on both sides, theta would be the inverse tangent of c. But since c is a constant, the inverse tangent of that constant is just another constant. So theta equal to a constant is the equation of that vertical half plane. Now I mentioned this idea of the half plane. The reason for that is actually right here. This hopefully makes sense when you think about what theta equals a constant would graph like. Every point on this plane is swung open the exact same theta value from the positive x-axis, or up here from this xz plane. If I extended my line back into the third quadrant, I would have a different theta value, 180 degrees further along, in fact. So we typically think of it as a half plane with a boundary on the z-axis. We don't extend it backwards. There's another real simple plane, the horizontal plane, z equals a constant. Again, we know what that looks like. If I've got some constant c here, that plane is simply at the constant height, c. Since z doesn't change in cylindrical coordinates, the equation is still z equal to a constant. These three surfaces, the circular cylinder, the half plane vertically, and then the horizontal plane, are known as the constant surfaces in cylindrical coordinates because literally it's what we get when we set each variable equal to a constant. I have a slightly prettier picture of that to show you, a little bit better than what I can draw. Let's see here. 1 second. There we go. Just had to shift my Word document a little bit. You can see in this picture that we've got our constant surface for r equals a constant. Here's the constant. They're labeling it with a slightly different Greek letter, but this is our theta. So this is our theta is a constant, the vertical half plane. And then over here is our z equals a constant, the horizontal plane. All right, there are a couple of other surfaces that are particularly simple in cylindrical coordinates. They're not constant surfaces, but they turn out really nicely, and I wanted to share those with you as well. What we'll call the half circular cone. Z equals a constant times the square root of x squared plus y squared. If you remember our quadric surfaces, this is actually the cone that opens around the z-axis. Because I'm using the positive square root, it's only the upward opening cone, not the other half. With a negative, that would be a downward opening cone. So this looks like that top half of the double napped cone. Let's think about what that would look like now in cylindrical coordinates. Again, the x squared plus y squared is simply r squared. And I can say the square root of r squared is r. since I'm only worrying about positive values of r. So z equals a constant times r, or r equals z technically divided by a constant, although that could just be multiplied by a different constant, will give me the equation of a half circular cone in cylindrical coordinates. Again, a nice simple equation when you compare it to the one we had to use in the rectangular coordinate system. Similarly with the circular paraboloid, if z is equal to a constant times x squared plus y squared, again, if you remember your quadric surfaces a little bit, this is that paraboloid opening around the z-axis. If I change to cylindrical coordinates by replacing the x squared plus y squared with an r squared, I once again have a nice simple equation. A little easier to work with usually than the one in rectangular coordinates. To the best of my knowledge, neither Maple nor GeoGebra have built-in graphers for cylindrical coordinates. Maple has a slight rudimentary one. We can graph some surfaces, but generally speaking, we'll actually use the rectangular form when we type them into Maple. But we'll use the cylindrical form to do our calculations, because as we're going to find out in just a couple of minutes, it's quite a bit easier. I do want to share with you a little bit of material from Maple here. If you can get your equation into the form r equals, it is possible to graph in Maple using something called cylinder plot. Notice I've got my width plots called up here, and then I've got the cylinder plot. This 4 that I had to type in first is automatically interpreted by Maple as r equals 4. So what we actually have here is this situation. R equals a constant, or r equals 4. And you can see that Maple did indeed plot a cylinder. If I look kind of down from on top, I guess I could change this to normal axes. Oh, only one L though. There we go. You can see that cylinder does have a radius of 4 if I look at the top down. Here's a cylinder plot for the cone. Again, this 2z is always going to be interpreted by Maple as r equals 2z. So I'm in this situation right here. R equals, as I said, z divided by a constant. Could be reinterpreted as a different constant times z. Right, dividing is just multiplying by the reciprocal. So I'm really in this case right here. R is equal to a constant times z. And I did set my theta values all the way around 0 to 2 pi. I set my z's as 0 to 3. I forgot to point that out in the previous one where we graphed the cylinder. And here's the plot of that cone, like we expected. These planes I can't plot with the cylinder plot, because notice there's no r in either equation, so it's not possible to solve for r, and therefore cylinder plot won't work for me. This one, if I worked at it just a little bit, I could solve this for r. I would have z divided by a constant equals r squared, and since I'm only worrying about the positive values of r would be the square root of z divided by a constant. I could pull that division by a square root of c out and make it a different constant multiplier. And my form would be r equals a constant times the square root of z. That's also workable on Maple. If I can get that up a little higher for you. There we go. And so here's my r equals, I just used a constant of 1 this time, so r equals the square root of z. Again, I've let theta go from 0 to 2 pi, and z from 0 to 5 this time. And you can see that parabola that's been plotted. So it is possible to plot in cylindrical coordinates in Maple, but only if you've got the form r equals something. That's a little restrictive. So as I said before, usually I will plot using the rectangular coordinates when I have a lot more flexibility, even when we're actually going to end up doing the calculations in cylindrical. All right, so that's part 1 of this 13.5a. We'll come back and do some examples in the next video.